I thought I'd start today's lesson by just going through one of the harder ones from 19E, actually two of the harder ones from 19E. So question 8 is the one that has that exact diagram, and it's about a fixed pulley, a cylinder sitting inside a loop in the, they call it a tape, and then a weight here that's free to move as well. First part of the question, A, if that cylinder moves down X, well, the first thing to notice is this side of the string needs to get longer by X, and this other side needs to get longer. For this object to move down to here, the string here needs to be longer by X here and X here, which means this one has to move up 2x. Okay, that means that if this one is falling with an acceleration of a, this one is rising with an acceleration of 2a. Now this is to do with the mechanical efficiency, the advantage we can get by using pulleys. Okay, so that's the starting point. Part C, now this is the best bit of the question. Find the tension in the tape in terms of G. Well, the way we're going to do this, we're going to add forces to the diagram. So this weight here, there's a tension there, and the weight of that object there. That tape goes up through the smooth pulley, around the smooth cylinder. So everywhere in the tape, we get the same tension. So acting on this cylinder, we get the tension acting upwards on that side and the tension acting upwards there. Okay, so T acts once there, T acts in both sides of the tape on the cylinder, and its weight acts downwards. So as soon as we've got that, the bulk of the mark should be for drawing a box around that object, and constructing the equations of motion. So they call it tape and box. So for box, Newton 2 downwards, 3g take T is the mass multiplied by the acceleration. For the cylinder, Newton 2 upwards, oh, got it the wrong way around, haven't I? Newton 2, that should be Newton 2 upwards, that should be Newton 2 downwards. Right, spotted my mistake, I've left space for it. So upwards, that's T take 3g is 3 times 2a. For the cylinder downwards, 8g take 2t is 8 times a. So it's the correct, I'm just going to check now, that's the correct acceleration, that's moving upwards. So upwards, downwards, upwards acceleration. This one's moving downwards, downwards take upwards. Right, can we find tension in the tape? I'm sure we can. So at the moment we've got simultaneous equations with one unknown, two unknowns. Right, what's the simplest way of doing this? We could rearrange to find A and substitute there, but I have a feeling, even though I don't need to find the acceleration, I'm going to rearrange to get, I'm going to rearrange equation 1 to make T the subject, so 6a plus 3g plus 3g. I'm going to sub into 2, 8g take 2 lots of that. Now I know that I've eliminated T and that's what I want to find, but I have a feeling that it might just be that little bit quicker to find the acceleration and substitute back into there. So I've got 8g take 12a plus 6g is 8a. 20a is 14g. So a equals 14g over 20, 7g over 10. I'm going to keep it like that until the very last minute. So I'm now going to put into this equation. Therefore, t is 6 times 7g upon 10 plus 3g, which is 42 over 10 plus 3, which I have a feeling I should be able to do in my head, but my brain at this time of night has gone to pot. 36 g upon 5, which is 36 times 9.8 divided by 5 equals 70.6. 9.8 so 71, I'm going to say 71 newtons, because why have I done that to 2 sig fig? Because g was to 2 sig fig. And let's just check the answer. So 19e question 8. 19e question 8. You know, if it's different, I'm going to say the book's wrong. 19e question 8. 2x2a 3.6g. Right. I don't entirely agree with that, so let's pause that. Right, so race to find the mistake here. Right, I think that's correct, I think that's correct, I think that's correct. Where do I tend to make mistakes? I tend to make mistakes where I, look, multiply out minus. Should that be minus 6g, which would make that 2g, which would make that g upon 10. 6g upon 10, so that's 3 plus 3/5 g, which is 3 3/5. 3 3/5 g. Okay, so that was that one. I'm just going to now draw the diagram for question 9 on the clean piece of paper and then go through question 9. So this is question 9. Let's see if I make a better go of this first time through than the last one. It's exciting, this, isn't it? Quite risky, as long as we say we never edit things. So a box of 10 kilograms sits on a rough table. So we're going to include, rough implies there'll be a frictional force, okay? But we haven't done all the work on friction yet, so this must be quite a simple way of dealing with it until we do the year 13 work. Attach 2 other boxes, mass 10, mass m, by 2 light inextensible strings. Smooth pulleys, so no friction at the pulleys. The system is in equilibrium, which implies forces balance. Given that the maximum possible friction between the box and the table is 49 newtons, so friction is 49 is the maximum it can take, okay? If the forces applied to this box here are bigger than 49, it will slide, okay? That's important. Find the range of possible values of m. Right. Now what I'm thinking is, if that's lighter than 10, the thing will slide that way. If that's more massive than 10, it will slide that way. Where am I going to start? It is a complicated question. I'm going to start with the forces. So there's a force, there's a weight of 10g. There's a weight of mg. Now there is, but it may be in this year, it's going to be irrelevant until we've done a bit of work in year 13. So there is a weight and there is a normal reaction, and they will balance each other, but we haven't talked about how that is connected to friction, so they'll be irrelevant. Right, there's two different strings, so this tension is not necessarily the same as that tension if the system was accelerating. So I'm going to put TA and TB there. If this mass is the heavy one, then this particle is going to be pulled that way, so the friction there is acting that way, but there is also this tension acting on that one. Those two tensions are the same. The force in the string, in this string, they're equal forces, but here it's pulling that one. Similarly, so this is M is less than 10. This one, M is greater than 10. I'm going to put all the forces on again, so a tension, but this time the frictional force acting that way. Oh, and the frictional force I know is 49 for the biggest this weight can be. Okay, we haven't talked about the relationship between reaction and friction, but we will find the biggest that can be is related to here. So, but we're told in this case it's 49. So what are we going to do? We're going to do balancing equations for each part of the system. Why balancing equations? Because it's in equilibrium. So I'm going to write for this one here, so let's call them A, B and C. For A, working vertically, TA must balance the 10G. So that tension is 10G. For C working that way, TA is balanced by TB and the friction of 49. For B acting that way, TB is mg. Well, how does that help? All right. Oh, so we know, isn't it? Right. So TA is 10G. So that's a 1, 2, 3. Right. 1 into 2. (10G) is 10B plus. Now, a bit sneakily, I happen to know that 5 times 9.8 is 49. So that 49 happens to be the same as 5G, which means that TB is 5G, which I put into 3, into 3. That means mg is 5G, m is 5. If this is the bigger of the two masses and it's just on the point of sliding, that's 5. Okay. So let's do the same thing on the other side. So if instead this is the bigger mass, as the biggest it can be, so it's still just in equilibrium, we've got TA is 10G. We've got TB is TA plus the 49. Actually, let's put that straight in, shall we? Right. So 10G plus 5G, 15G. For B, TB is mg, TB is 15G, m is 15. So if this frictional force is as big as it can be, 49, we found the smallest that mass that can be. If that were any smaller, 49 is still the biggest friction, but this one will then pull everything that way. If this is any bigger than 15, everything will be pulled that way. M is between 5 and 15. Right, that's a good one. Hope you enjoyed those. Right, what am I going to say? Aside from the mistake, what we're looking for is diagram with forces, a statement of what you're doing. In this case, it's Newton 2. If need be, number these so you can say what you're doing. Write it clearly enough so if you do have a mistake, you can go back and find where you've made the mistake. Diagram. Somewhere write down the assumptions, what you're told. Equilibrium. What does equilibrium mean? It means we balance the forces everywhere. And once you've written down the simultaneous equations, explain what you're doing. Whether it's write all three, then solve them, or work your way through and solve them. Okay? This is the bulk of the marks, establishing the equations. What I want you to do today is, from mixed practice 19, just working way through the even ones would be fantastic. Ask me about the ones you want to go through. Next week, we're going to start looking at some exam questions on all sorts of the topics we've done.